Hello and welcome to lesson 40 of my DP chemistry curriculum. Today we're going over structure 2.2.3, which discusses coordination bonds. We will talk about how they're a covalent bond in which both electrons of the shared pair originate from the same atom. We'll be able to identify coordination bonds by the end of this lesson. And if you're an HO, we did already discuss transition element complexes in lesson 33, where we talked about properties of transition elements. When we talk about colored complexes and often in aqueous solutions or when we're forming complex ions, those metal cations are making coordination bonds with those ligands. So if you need a refresher, go back to lesson 33. Now, what is a coordination bond? Well, we already know that a covalent bond, which a coordination bond is, a covalent bond is just a shared pair of electrons. It can be two electrons, four electrons, or six pairs of electrons, but they share them equally. One atom gives one atom gives another. But that's not always the case. In a coordination bond, what actually happens is it's a covalent bond where both electrons come from one atom. And we have to meet a couple conditions for a coordination bond to work, but a couple things to know is that these act the same as a covalent bond, which means there's no actual difference when it comes to properties. Strength, size, all that will be exactly the same. Now, I said we had to meet some conditions. So first, what we need is a donor. A donor does have non-bonding electrons available for bonding, essentially. So something like hydrogen has no non-bonding electrons. When we look at like hydrogen, it has one electron that bonds, so it could not be a donor. However, something like oxygen, while it usually makes those two bonds, has these two awesome pairs of non-bonding electrons right there. And oxygen makes a really good donor for coordination bonds. So oxygen gets the check mark. We also need an acceptor. An acceptor, much like a donor, but the opposite, has has space for a pair of electrons. And what I mean is it still needs to fill an octet. Needs to fulfill an octet. So we can get many acceptors, anything that isn't really doesn't can't make the extra bond but needs more electrons. So let's start with an example. A good example is carbon monoxide. Carbon monoxide. Now, you may already know what it is, but from the name, we know that it is one carbon and mono meaning one oxygen. So if we were to draw this normally, you might draw carbon. We know it has four valence electrons. Oxygen has six. And I'm just drawing Lewis dot diagrams of them. And if we were to do our standard way of doing this, we would maybe have carbon single bond to oxygen. We know we have four valence, six valence. So we'll add another 2, 4, 6, 8, 10. And that's all the electrons we get. So following our protocol, we might maybe go ahead and move this here. So when we do that, we are still generating electrons from each. And you may already recognize that we can then move this over here and bond it up there and make a triple bond. But the odd thing here is that carbon only starts with four valence electrons. So if we were to draw this out but now have different colors, carbon 1, 2, 3, 4, and oxygen we'll put in red still, 1, 2, 3, 4, 5, 6, oops, 5, 6. As we make that bond, that first bond is going to take part with 1 carbon, 2 carbon, and over here we have oxygen, 1 oxygen, 2 oxygen. So that first bond, that double bond, is going to use up carbon's electrons. Carbon will still have a pair. But if carbon donates one of its electrons here to this, whoops, and oxygen donates one of its electrons here, carbon still only has 7 valence electrons. And oxygen will have 6, 7, 8, 9. Oxygen will have 9 valence electrons. So this structure right here does not work. So it turns out the way it does work is if oxygen donates both electrons for that third bond. And now in this case, we have 8 valence electrons and 8 valence electrons. So in this case, we have 2 covalent bonds, 2 regular covalent bonds, and 1 coordination bond. So this is a triple bond with 1 being a coordination. So we have to be able to recognize where those electrons are coming from to make these bonds work. Now, when we actually draw this diagram between carbon and oxygen, it would just look like this. There is no difference. Like we said before, there is no difference in valence electrons or Lewis dot diagrams or covalent bonds. A coordination bond acts exactly the same. But we must identify that one of these would be a coordinate bond for the DP exam. So how do we actually represent coordination bonds? Let's learn. So representing coordination bonds. There's 2 general ways. Number 1, treat it the same. Treat as covalent. And that's exactly what it sounds like. We don't make any changes. That's what that carbon monoxide is right there. We don't represent it. We just understand that one of them must be via the way valence electrons organize themselves. The second way, which is far less often used, is using an arrow from donor to acceptor. So we can redraw carbon monoxide as 2 bonds and then an arrow. And this would represent this top one as our coordination bond. And so that is a way that you can represent it. It's much easier to do it when you're using single coordinate covalent bonds. So for example, in the case where we have ammonia, which looks like this, and we react it with boron trifluoride, which, if you remember, boron trifluoride has an incomplete octet around boron, and it looks like this. Now, boron has this open space, so boron is the acceptor, while nitrogen's going to be the donor. And so when these form a bond, you could write it in both ways. We could write it just simply NB with our H's and our F's, and pardon my laziness here, I'm not going to draw the bonds around the F's, or you know what, I'll be lazy but not extra lazy. We'll do lines. Or you could, for instance, use the arrow from the donor to the acceptor. And this would also be a fine way of writing a coordinate covalent bond. While both are acceptable, you'll tend to see this more often in your DP exam as well as in the real world. Nobody usually cares to draw an arrow to identify a coordinate bond. We just accept them as coordinate bonds and walk away. So the last thing we'll do is a little example. So let's try and do hydronium, H3O+, which is formed by the reaction of H plus, so a hydrogen ion and water. So you can try this on your own. If so, pause the video. Otherwise, I'm going over the answer now. H plus is simply drawn as an H with no electrons. So it does have that open space. This is going to be our acceptor. Meanwhile, H2O is simply drawn as such, and this oxygen is going to be our acceptor, or sorry, our donor. So this oxygen has this couple non-bonding pairs, and we can just pick one. And so what we're going to get is a bond via those. So this will become H, O, H, H with that pair. However, something you have to keep track of is we did have a positive charge, and this whole thing is now positive. So much like our polyatomic ions, we need brackets and a plus. These are these little things that will get you on the DP exam that you have to be careful for, because while you may be able to draw the structure, forgetting to put the brackets and the plus will lose you the mark anyways. Anyways, I hope this helps you learn a bit more about coordination bonds or coordinate bonds or coordinate covalent bonds, lots of ways to call them. And anyways, have a great day.